So good afternoon or good morning, everyone, depending on where you are. Thank you very much for joining us today to our GEO at EFR Seminar Series 2024. Today, we have a great pleasure to welcome Dr. Diana Roman, who is HE Chair of Seismology in Carnegie's Earth and Planets Laboratory. And she will discuss the seismic characterization of volcanic systems. So, Diana, the floor is yours.
Okay, thank you so much. Good afternoon, everybody, and thank you for coming. Just before I dive in, I want to make a few comments about this talk. The first is that I was invited to talk about volcano-tectonic seismicity, but as you'll see in the talk, it's really critical when studying volcanic systems to use as many types of information as possible. And so you'll also see me discuss other types of volcanic seismicity. I'll introduce this. As well as other measurements that we can make at active volcanoes. And really it's the synthesis of these different pieces of information that leads to insights into how volcanoes work. The second very important thing I want to point out is that even though it's only my name on this title slide, this talk is really a very thin veneer over an ocean of efforts by other agencies, research groups, and I really want to acknowledge the efforts of the monitoring agencies and the research groups and thank them for providing their data openly so that we can do sort of meta-analyses like the one that I'm going to present today. So let me start with a general motivation. So I'm a research scientist, but really in volcanology, we're always trying to understand volcanoes with an eye towards doing a better job of forecasting eruptive activity. And what we have some ability to do is say when a volcano is likely to erupt, if it's monitored instrumentally. And we can also make generally statements about, the possible timing of that eruption and that again depends on the volcanic system, how well that can be done, but it's ultimately a goal that we would like to have to say more precisely when, if a volcano seems likely to erupt, when that eruption would be. But also we want to think about the longer term. We don't just want to know, usually we see that volcanoes show activity anywhere from hours to months, in some cases years prior to their eruption, but we would also like to know which volcano in a region is going to erupt in the coming decade, and that's more of a challenge. I won't really get into that today. We'd also like to know more about, in advance, what style of eruption and what hazards that eruption will pose, and generally, will the eruption be explosive or will it be more effusive, because those are very different hazards. And we'd also, of course, like to know during an eruption, how long is the eruption going to last, and will it change its behavior in the middle of the eruption? I'm not really going to talk about that one today. And I just want to put up one example here, which is the recent series of eruptions on the Reykjanes Peninsula, which is a case where there have been actually really phenomenally precise forecasts of actually the short-term timing. But there have also been multiple challenges, and you can see that illustrated in these two articles. In November, the volcanic system started to show signs of unrest that looked like it was immediately poised to erupt, and that eruption actually didn't happen immediately. But after several additional weeks, there was an eruption. It was forecast and people were evacuated successfully. But there were also other questions about where the eruption would occur, and that led to challenges in terms of both, will it be threatening power plants or villages, or will it occur offshore and perhaps involve seawater that would make it more explosive rather than the effusive activity that actually did occur. So what we're trying to do really is a comprehensive forecast of volcanic eruptions. So what I'm going to do in this talk, I'm not going to address all of that. I'm going to do this in two parts. Part two is a bit shorter. The first thing I'm going to do is talk a little bit about how we use volcanic seismicity and some paradigms of volcanic seismicity to understand the short-term likelihood and timing of eruptions. And I'll go through a series of case studies looking at patterns of seismicity before 3 eruptions in the United States, and what they actually tell us about how the volcano might work on both the short time scale and a bit on the longer time scale, and how that might inform how we could make better forecasts. And then the second part, I'm going to talk a little bit more about how volcanic seismicity might give clues in advance to the eruption style by telling us about the bulk viscosity of the magma that is driving the unrest. And so I'm going to talk a little more about the theory of dike-induced stress regimes, and what we can observe in terms of stress changes by looking at earthquakes that can tell us about the viscosity of magma. And I'll go through a series of case studies again and sort of synthesize the state of the art in the open questions. Okay, so diving into part 1, I just want to start with a few pretty well-established paradigms about volcanic seismicity. And the first paradigm is that, assuming that there are instruments close enough to the volcano, we see seismic unrest prior to eruptions. This is the basis of my career and a pretty reliable thing. And so this is one of the reasons that if a volcano is instrumentally monitored, it tends to be monitored by seismometers, because this is a very reliable precursor to eruptions. So just as an example of this, I'm showing you, this is from the Alaska Volcano Observatory, some time plots here over multiple decades from a volcano called Augustine that has had several eruptions since it's been seismically monitored. So what you're looking at is time on the x-axis, the number of volcanic earthquakes per week on the y-axis. So these are the black bars here, and then the red bars here show you 4 eruptions. And what I want you to see is that prior to each one of these red bars, one of these eruptions, we see an increase in the number of earthquakes. So that is a very nice example of seismicity preceding eruptions and being useful as a precursor to eruptions. The second paradigm is that when we monitor seismicity at a volcano, we see a number of different types of seismic events. And so volcano seismologists spend a lot of their time classifying events into this whole zoo of different classes, with the idea that the class of the seismic signal is actually reflecting a different type of process within the volcano. So the nature of the seismic signal reflects the underlying physics of the source process that caused that seismic event. And there are a lot of different classes and different terminology. It's a bit of a mess, but just for the sake of this talk, I'm going to basically be talking about what we call VT, volcano-tectonic or high frequency earthquakes. So you'll see an example of one here. Here is basically what you see on the seismometer, which is this little wiggle here. That's the earthquake. And then on the lower panel here, you're seeing a spectrogram. So you're seeing the distribution of energy during that earthquake in time. And VTs are characterized by this higher frequency, more broadband frequency energy. They are basically the same thing as tectonic earthquakes. They have P waves and S waves. They generally have mechanisms that reflect stick-slip behavior. So we relate them to the breaking of rock under stress. And then the other type of volcanic seismicity, very generalized, is what we refer to low frequency or long period LP or LF seismicity. And an example is here on the upper right. You'll see some other sort of hybrid long period and a VLP, and there are many more classes. But in short, you can see again here the earthquake, and you can even see by eye just in the raw seismic data that it's a little lower frequency. And you can also see that very clearly in the spectrogram below, that most of its energy is really below 2 to 3 hertz. And so there are a lot of different models, much less clarity on exactly what the process is for this type of seismicity, but I'll just generalize and say most of the models tend to point to the involvement of some sort of degassing or fluid circulation, some sort of resonance process. So we tend to relate these more to the involvement of volcanic gases or enhanced fluid circulation due to heat or degassing of the magma. Okay, so here's an example of what this looks like in precursory sequence. So on the bottom panel now, you're looking at a time spectrum figure from Seth Moran at the Cascades Volcano Observatory. And this is the seismicity that was observed prior to and at the very beginning of the 2004 eruption of Mount St. Helens. And so what you can see here is that at the onset of seismic unrest, it started with high frequency events. So you see that the energy is sort of around 15 hertz. It's quite high. These are rock breaking type events. And then shortly before the eruption actually began, we started to see much more of the low frequency seismicity. So this is a sort of paradigm sequence evolution of starting with high frequency seismicity prior to eruption and then seeing more low frequency seismicity. Okay, so we could put those things together into this very simple model of what we might expect in terms of seismic behavior prior to an eruption. So very simply, we start with a volcano that's in quiescence, it's asleep. Somewhere below it is a magma reservoir. We can get the depths of those reservoirs after the eruption by looking at petrology, looking at how much water was in mountain inclusions and other tools. So as the reservoir begins to pressurize and start to basically form a conduit connecting to the volcanic edifice, we might first expect to see deeper, higher frequency earthquakes, as this is still at several kilometers depth. There's not a lot of gas exolving at this point, and we might expect some upward propagation of the seismicity. And then at some point, and this might be accompanied by something like surface deformation that reflects pressurization at deeper levels, maybe some deep degassing, more dominated by CO2 than SO2. And then as the magma moves upwards, we might expect a transition then as the magma experiences lower pressure from the overlying rock, begins to exsolve its volatiles. We might start to see more shallow, low frequency events. And we might also see deformation, more focused, suggesting a shallower magma that's moving upwards. We might see changes in the composition of gases that reflect this shallowing of the magma. And then finally, we would expect to see the eruption. So this is a very sort of idealized sort of guess or intuitive model for what we would expect prior to a volcanic eruption. So there are a few problems with this model. The first of which is the false alarm problem. And so what I'm showing you here, again, a figure from John Power at the Alaska Volcano Observatory, is basically now in time over several decades, since the start of seismic monitoring in Alaska, the formal start of seismic monitoring in Alaska at volcanoes, the number of earthquakes throughout the entire arc per month over time. And there are some changes in this curve. So we're basically, it's not breaking apart individually, it's just saying the entire catalog, how many earthquakes. And there are some changes, some increases that reflect maybe the increase in instrumentation, new volcanoes having instruments on them. But you see these spikes here. And these spikes all correspond to specific volcanoes as labeled. There's the Augustine 2006 that I showed you earlier, so big spike, readout 2009. But there are a lot of spikes in this plot that are related to volcanoes that did not ultimately erupt. And so these are all the ones that I've put red boxes around. These are all so-called false alarms, where we saw an increase in seismicity and the volcano then went back to sleep without erupting. And so these are quite common, and we really have currently no good tool to distinguish when there's an episode of seismic unrest in a volcano. Is that going to proceed to eruption or not? It's a big open question and a big challenge. Okay, and there have been several attempts. This is something that is quite common at volcanoes around the world. There have been several attempts to quantify the rate of false alarms versus, true precursory sequences. And so these are just a few examples. On the left here, looking at the color code changes that AVO has assigned over the years. So volcano monitoring agencies generally use a traffic light system of yellow being a warning, unrest, red being eruption, orange being eruption. And so this study basically looked at how many times a volcano was elevated to yellow, and then what happened afterwards. And of all of the increases from green to yellow over many decades, more than half of them ultimately went back to green without any eruption. So this is about a 50-50 chance estimate that an episode of unrest will be a false alarm. And similar numbers have come from studies of global analyses of INSAR deformation. This is a really great paper by Juliet Biggs, coming up with about the same number of true positive versus false positive for deformation episodes. And then I've recently started to work on a global study of trying to expand the Cameron study, and I'm coming up with about the same number. So it seems like most studies say that about 50% of episodes of seismic unrest deformation do not ultimately culminate in eruption. The second issue, coming back to this idealized intuitive cartoon, is that we generally don't see seismicity prior to eruption shallow with depth prior to the eruption. And so I'm aware of exactly 2 case studies in the world where this behavior was observed clearly. And the first is from an eruption at Piton de la Fournaise in the Indian Ocean in 1998. And you can see these are little time chunks leading up to the eruption with depth. And you can see that the seismicity, the black in each plot, each box is the current seismicity for that period, and the gray is the previous seismicity. And you can see this very nicely upward propagating seismicity that makes it about into the edifice before the eruption starts. Okay, so that's example 1 of 2. And just a few years ago, the number doubled because something similar was observed prior to the onset of eruption at La Palma in the Canary Islands. This is a paper by Luca Dauria. You can see the long-term pattern of seismicity prior to the eruption and after the eruption here, but zooming in on just this period of about 10 days immediately before the eruption, you see this very nice upward propagation of the seismicity prior to the eruption. So these are very exciting, beautiful, they're intuitive, but I will tell you that they are very, very uncommon. Most volcanoes do not show this upward progression prior to eruption. So what I'm going to suggest is that we can actually resolve these 2 issues by taking a longer term view of what's going on prior to an eruption, and really looking at ideally the decade or the entire cycle from the previous eruption to the current eruption. So what I'm going to do now is I'm going to go through in much more detail some time depth patterns of seismicity, deformation, and gas prior to eruption. And I'm going to pose a model that addresses these 2 issues and ultimately ties them all together, and also potentially tells us a clue as to what we might use to do a better short-term forecast of exactly when, once a seismic sequence occurs, the volcano will erupt. So I'm going to focus on 3 volcanoes, 3 eruptions that in some ways are very similar and in some ways are very different. So 2 of these are in the Aleutians, Redoubt and Okmok, and one is our famous case study of Mount St. Helens in 2004. They're all very well monitored volcanoes with long-term networks of monitoring, so we can really look at their long-term behavior. They have very similar duration prior to their eruption, so they tend to be in repose for about 1 to 2 decades between eruptions. So they generally are about the same kind of cycle duration. Somewhat similar compositionally, but the big difference in them is that there are orders of magnitude, 2 orders of magnitude difference in the duration of the unrest prior to each one of these eruptions, ranging from Okmok 2008, which only had 5 hours of precursory unrest, through Mount St. Helens, which was again fairly short. It had a little over a week of unrest immediately before its eruption. And then to Redoubt, which had almost a year of unrest prior to its most recent eruption. So we want to look at, in some sense, why, and is there something useful that might help us anticipate for a given volcano when we start to see unrest? Is it going to be very short like Okmok, or is it going to be very long like Redoubt? Okay, so I'm going to go through each one of these. And what you'll see in 2 out of the 3 of these is this problem of us not seeing seismicity move upward consistently prior to eruption from where we think the magma was sourced to up to the vent. And in fact, we generally see the opposite. We see that the earliest seismicity tends to be extremely shallow in at least 2 of these cases. So we see like a top-down migration of seismicity rather than our intuitive expectation of bottom-up. So here's Mount St. Helens. These are all going to be time depth plots, so time and then depth, and then all these little dots are individual earthquakes, and then I'll put the color code change up top. So again, this is a very short sequence. It started with very shallow seismicity. The magma was sourced from somewhere from 3 to 8 kilometers depth. That's pretty well constrained by petrology. So there's an issue here of why don't we see seismically the magma coming from the depth where we know it was originating from, and why do we only see shallow seismicity? So same problem at readout, where there was a very long, almost a year-long duration of precursory seismicity, and this was a very confusing precursory sequence. You could see the the toggling of the color codes here before it finally erupted here. But what I want you to see in this time depth plot are a few things. So the source depth of the magma from petrology is a little less well constrained here. It's maybe 2 to 3 kilometers. But the deformation that was observed prior to this eruption, which was very poorly constrained, it was not a volcano that had good geodetic monitoring, was the first, not only the first sign of unrest over a year before the eruption, but also it looks like that unrest was very deep. But then when we look at the precursory seismicity, we see another interesting thing here, that the seismic unrest actually started with long period seismicity. So not, again, as in our intuitive model, starting with rock breaking VT events and then moving into lower frequency events. So we start with low frequency events. We eventually start to see the high frequency events here, but again, they're very shallow, above where we think petrologically the magma was sourced and geodetically where the magma was sourced. But ultimately, we see this top down where eventually the seismicity late in the precursory sequence during the onset of eruption, and then as the eruption progressed, starts to reach the depths where we think the magma source region was. So this is weird. And then with Okmok, which was 5 hours of precursory unrest, we again see a mismatch between the petrologic and geodetic storage depths, which are here. So petrologic, it looks like there are a few different reservoirs, but again, sort of in the mid to upper crust, and the geodetic storage depth somewhat in the upper crust. But when we look at the precursory seismicity, it's actually much deeper here. So this is maybe more arguably a bottom-up seismic sequence, but again, only 5 hours of seismicity, and really across all depths. So there isn't this good connection that we would expect to see between where the magma we think was and where the seismicity is actually occurring. So we have to resolve all of these problems. So to address these mismatches in our intuitive understanding and what we actually observe, and the disconnect between where we think magma was sitting for petrology and geodesy and where we see the seismic activity that we think that magma is producing, we put forth a 3-stage model. And the model is basically starting with a stage of staging, where the magma, some amount of magma has to move up into the shallow level of the system, because that's where we often see the earliest seismicity. So the first magma that generates seismicity before an eruption has somehow at some point in time gotten up to a very shallow level without necessarily producing appreciable seismicity that tracks it. So that's staging, and I'll talk about a few different mechanisms for staging. That staged magma, that shallow magma, then becomes destabilized through some mechanism, and it starts to generate the first seismicity that we see before an eruption. And then ultimately, that destabilization is what leads to the onset of eruption. And in many cases, we then actually see a tapping phase where we start to see seismicity move deeper into the system, which suggests that now the eruption is starting to be fed by the main reservoir. So the implication is that we have this kind of stealth magma, maybe small volume that's snuck up here, and that's what really drives the precursors and what actually comes out first and starts the entire sequence, leading to an ultimate evacuation of more of the main magma body. So I'm going to focus on staging. And there are a few different mechanisms that are not mutually exclusive that we might invoke to explain how this initial batch of magma gets to shallow depths and starts to drive seismicity. One is simply that that's leftover magma from the previous eruption. It's just been sitting up there, and through some process, it starts to pressurize, maybe through second boiling as it cools and crystallizes. And that's simply just a time process that's involving magma that was left at shallow depths in the last eruption. Another possibility is that we have somewhere in between the two eruptions, we have a more focused quantum of magma that actually comes from the main reservoir. And so we might actually relate these to some of these false alarms that I mentioned. So these false alarms might actually be delivery or staging of magma that doesn't ultimately erupt, but that eventually gets to a point where it starts to drive the eruption. And then finally, another possibility is that we have this volume of magma, this small volume of magma, or maybe even the main volume of magma, moving up at a fairly slow rate. And that rate is slow enough that it doesn't produce sufficient strain to drive seismicity, but it is moving upwards. So this may be an aseismic staging that occurs more gradually prior to the eruption, but ultimately immediately before the eruption. So slow intrusion or aseismic staging is another possibility. But we might expect, if it's a larger volume, some longer term geodetic signal for this, even if it's not going fast enough to drive seismicity. So this is our model. And now I'm going to go back to those 3 case studies and talk about what additional clues we have from a longer term view and which of these mechanisms might have been at play. Okay, so now we're going to zoom out in the time depth plots. So instead of just looking at the immediate precursory sequence, you're going to see the bigger picture, the full cycle, or as far back as we can go. So coming back to Mount St. Helens, again, this was about a week of precursory seismicity, very shallow. The red here is the 2004 eruption to 2008. The red over here is 1980 to 1986. The petrologic storage depth is down here. Again, you see this disconnect in the early seismicity from where we think the magma was sourced. But now, if we look at what happened seismically between the 2 eruptions, we see these 2 very strong swarms of earthquakes. And in fact, this second one was actually accompanied by some surface, very, very minor explosive activity. And so these 2 seismic swarms are thought to be intrusive events, false alarms. And those are potentially the mechanism by which magma came up from this main reservoir, was delivered to the shallow reservoir, and then sat for several years, and eventually got to a point where it was pressurized enough to start seismicity and ultimately drive the eruption that eventually came and tapped deeper levels of the system. So consistent with this idea that this is the staging mechanism, I'll also point out that there was very negligible deformation observed prior to this eruption. So it didn't seem like there was something that was sneaking up, or at least a large volume that was sneaking up aseismically, because we didn't see deformation. And because we didn't see deformation during these 2 episodes, this was probably a fairly small volume of magma, but it was sufficient once it was staged at this depth, to eventually reach a point where it could start to break rock and ultimately destabilize the system into eruption and connect it to the deeper reservoir. Looking at the gas data from Mount St. Helens prior to both of its eruptions, we also see evidence that this was what occurred. So this is the gas data, the SO2 data between the 1980 onset and the 2004 onset. Unfortunately, there was a period here where there was no gas data. This is the same for the CO2 from 1980, again, up to 2004. Very limited data, unfortunately. But what both of these show, at least in the early, is that there isn't a lot of evidence for big amounts of gas coming out of the volcano in between its eruptions. So this magma, when it came out in 2004, was actually pretty flat. It didn't have a lot of gas. And again, that's quite consistent with it having sat for a long period of time, maybe bleeding off that gas very slowly at a shallow level, and also maybe being a fairly small volume of magma. So there's still sort of a question about the mechanism of how this small volume of magma all of a sudden was able to destabilize and create this whole large eruption sequence. I'm not going to go into that. One possibility is there may have been some additional magma that, finally set it off to a tipping point where it could start the eruption sequence. But the conclusion here is that the 2004 eruption of Mount St. Helens was really triggered by a small volume magma injection, even though ultimately it erupted a large volume of magma. And we think that that small volume injection happened several years to almost a decade prior to the eruption sequence. Okay, looking at readout, we have a very different story. So again, this is the longer term view. This is the 2009 eruption of readout. This is the 1989 to 1990 eruption. And what we see in between these two eruptions is that there really isn't evidence like there was at Mount St. Helens for these strong injections, these false alarms. So we don't see evidence that the staging was done in discrete intrusive episodes prior to this eruption. And again, I'll remind you, this was a very long duration run-up. It was very confusing and complicated. It seemed to involve several levels. And our suggestion is that this was a case where we had the long duration run-up without much going on in between eruption because we had this slow aseismic staging. And again, I'll remind you that we did see evidence for deformation early on during this precursory sequence. We did not see a lot of seismicity, but we sort of saw this complex sequence of unrest. And so we think that this may be a good example of quiescence between eruptions, but then a long period of some volume of magma moving up aseismically immediately prior to the eruption. When we look at gas and now thermal data from prior to this eruption, we see additional evidence that this is what happened. So complicated plot. But the short takeaway here is that there was very high CO2 observed very early on in the precursory sequence, so suggesting some involvement of deep magma, and that remained high. So this may have been a larger volume that came up aseismically. We saw some changes in these ratios immediately prior to the eruption, but also they remained high during the eruption. So again, suggesting maybe a larger volume that came from depth, but came up aseismically over a longer period. Similarly, some really interesting new data from thermal satellite observations shows that the volcanic edifice began to heat up early on in the precursory sequence as well. So again, this is maybe another clue that this was a fairly large volume of magma that started to move upwards very slowly over a long time period before the eruption onset. Okay, and then the final example. So here we have the eruption, again, triggered primarily by aseismic eruption, aseismic magma ascent immediately prior to eruption. Okay, and then the final case study is the short precursory sequence. This was the 5-hour sequence prior to the 2008 Okmok eruption. So one interesting thing about Okmok is that it is constantly inflating. And it has this very well-known and well-studied inflation-deflation cycle. And so you can see over a very long time period here, this was the 1997 eruption. Unfortunately, there were not seismometers on the volcano at this time, but immediately after this eruption, Okmok began inflating. And it started to level off in terms of inflation prior to the 2008 eruption, but it sort of constantly inflating. And so one possibility here is that we've got, again, aseismic, we think, consistent feeding of a shallow reservoir that begins essentially immediately after the last eruption is over. So this is somewhat of a combination of the intereruptive being important, but also being a fairly slow process. So if we look at the precursory seismicity again, you'll see that there really wasn't much going on until very shortly before the eruption. So an interesting question here is what triggered this eruption when it happened. So we see that probably there was something that was placing a fairly large volume at shallow depths from the deformation, but we see that the seismicity is quite deep immediately before the eruption. So this is a possibility that basically we popped the balloon with a small volume, very rapid injection of magma immediately before the eruption, and there was a large volume there that had already pressurized, and so that was the mechanism by which this moved into a fairly large eruption with very little precursory seismicity and a sort of complicated combination of depths being involved. So again, a small volume coming up into the main volume, essentially popping the balloon in the upper crust, and then a very rapid movement into eruption. Okay, so taking all of these three case studies, and again, coming back to this question of how can we do better about saying not just when a volcano becomes seismically active that it's likely to erupt, but maybe how long until it erupts. It appears that there might actually be, if you take these three case studies together, a possible relationship between the amount of time a volcano spends in some unrest state during its intereruptive period and how long the immediate seismic precursory sequence is. So from Okmok, which spends almost all of its intereruptive phase in geodetic unrest and has very short precursory sequences, to Redoubt, which is actually very quiet during its intereruptive phase, but then has very long precursory sequences, and St. Helens being in the middle. And there are a lot of factors that might also go into the control on why you get short precursory sequences at some volcanoes and long sequences at others. But I think this is one that has not yet been considered, and there are certainly exceptions, but I think there is growing evidence that the amount of damage perhaps that happens in the rock due to this intereruptive unrest might have a fundamental control on how long that seismic sequence will go before eruption. So we might actually be able to use that by looking at, was the volcano very active in intereruptive period? We might expect a short sequence versus a quiet volcano, we might expect a long sequence. And this actually ties into some interesting recent numerical modeling work that looks at the rate of injections into a magma chamber and whether those injections are at a sufficient rate to actually tip this numerically modeled volcano into eruption. So this is kind of building on this numerical work. Okay, so let me summarize part one, and I see that I'm already 40 minutes into this, so I'll go through part two fairly quickly. So part one, the key implications are that the eruption triggering process can actually begin years to decades to perhaps centuries prior to an eruption. And it's really critical to take this longer term view of geophysical unrest in terms of how magma is moving within the system and how the volcanic system might move into eruption. That triggering process, that staging, may in many cases actually involve a very small volume of magma or a very slowly ascending volume of magma. And that may account for most of what we can see geophysically or what we don't see during both the long-term unrest and the immediate destabilization and unrest before the eruption. And so what I'm trying to argue for here is that we really need to focus on decadal scale and multi-parameter observations to understand fundamentally how volcanoes move through their cycle and move into and out of eruption, and how these false alarms might actually be an important part of our forecasting efforts. Okay, so I'm going to move into part two here, where I'm going to talk a bit about how we can use volcanic seismicity as a precursory indicator of magma bulk viscosity, which is a fundamental control on whether the volcano erupts explosively or effusively, and the hazards that are associated with that. I'm going to go through some very brief theory on the stress regimes and the mechanisms of faulting that occur during dike emplacement in solid rock, And then I'll show you some case studies that tie fault plane solutions for VT earthquakes into bulk magma viscosity. Okay, so I'm going to start with a numerical model from Alan Rubin and Dave Pollard's work. Fairly old one, but I think this is a phenomenal basis for understanding a lot about volcanic VT seismicity. So this is a dike, and in this case, you can consider it either moving upwards or sideways. But basically, what the model shows is that this dike, as it pressurizes and propagates, generates two stress regimes within the surrounding crust. The first regime is in the walls of the dike and is compressive. So we actually see a modeled increase in compressional stresses as this dike pressurizes and opens. A second regime occurs at the tips of the propagating dike, where we see the opposite, that we expect an induced stress regime of tension. So there's a dilation in a volume of rock ahead of the tip of the dike. So I'll talk about wall stresses and tip stresses, and I'm primarily going to focus on wall stresses. So this is the numerically predicted stress regime, and we can actually interrogate the stress regime by looking at fault plane solutions for VT earthquakes. So I'll talk you through a little bit about fault plane solutions here and what the key things to look at in the case studies are. But basically the theory here is that if we have a dike that's in place, it will want to open in the direction of least resistance. So in doing that, whatever the ambient stress field is induced by tectonics, the dike's tendency is always to open in the direction of least minimum compression. And in doing so, dikes tend to align themselves with the maximum compression orientation. So in a subduction zone, we tend to see dikes that are parallel to the plate convergence vector, for example. And the theory is that in dilating in the direction of least ambient compression, this local stress field, that's this compressive stress field, the wall stresses, can actually rotate the sense of slip on an earthquake. So this is our VT earthquake. And the simple model basically predicts that we would see a rotation in the P axis, or the pressure axis, of the fault plane solution for the earthquake, such that it is nearly parallel to the fault plane solution for an earthquake that would occur in the ambient stress field away from the dike, or during a period where there is no dike pressurization in the rock. So we're looking for this, what we call a 90-degree rotation of the VT fault plane solution. So don't worry about fault plane solutions if you don't know much about them. We basically constrain them by looking at the polarities, the first motions of the VT earthquake, something like this. And from that, we can fit two candidate nodal planes that tell us approximately where the stress that produced that earthquake, the maximum compression, is. So all you need to worry about here is this orientation of the P axis. That's our proxy for this compressive regime versus the regional compression. And what we're going to be looking for are rotations in the position of this P axis. And I'm actually going to show these to you as these Rose diagrams of P axis orientations. And I think in all cases, I'll mark where the ambient compression is. So what we're looking for is a deviation by about 90 degrees. That's an indication that we have a dike that's inflating in the crust and changing the nature of seismicity, the VT seismicity. Okay, so that's a very quick run through the theory. And what I want to show you is that when we do this, when we look at fault plane solutions for VT earthquakes, we see very commonly this 90-degree rotation. So this is Superior Hills, which was a long-term eruption. This is just one example. The orientation of maximum compression is here, so southwest, northeast. And prior to major changes in activity, when the volcano comes out of a pause of activity, so this is D here, we see this rotated sense of P-axis orientation, okay? And we don't see it during periods where the volcano is quiet, or we don't think there's a lot of pressurization. So this is a really nice indication for us that these earthquakes are actually responding. They're basically breaking in the walls of the dike in response to those wall stresses that are induced by dike inflation. And this is something that we can look for in VT earthquakes. Okay, but we don't see that everywhere. So this is a very famous example from an eruption at Holuhraun in Iceland about a decade ago, where we saw, in this case, a very nice lateral propagation of the seismicity to the eventual eruption site, but the fault plane solution showed no rotation. So what you should look for is that the white quadrants of the fault plane solutions are generally roughly aligned more or less with the orientation of the dike. So this is a case where we don't see that 90-degree rotation. And that's interesting. We want to understand why we see this rotation at some volcanoes prior to eruption and not at others. So if we go and look at all of the studies that have ever been done with well-constrained fault plane solutions prior to eruptions, this is the list. So this is the eruption, its composition, its tectonic setting, and whether somebody observed this 90-degree rotation or not. You see that there are quite a lot where this phenomenon has been very well documented, but there are many where it has not, including Holuhraun. And as a first order of what the difference is, it appears to be compositional. So you see this line where we don't see this rotation, tends to be much less evolved magma, basalts, maybe basaltic andesites. And where we do see the rotation tends to be more evolved, more silicic magma, andesites or dacite. But there's sort of some mixing here. There's a bit of an issue. So at Etna, there was a rotation in 1991 and several other studies since, but it's a basalt. But when we look at the actual composition of the rocks and the textures of the rocks that were erupted, while it's ultimately a whole rock basalt, it's highly, highly crystalline. This is a very wet magma. It was very crystalline. So even though this was a basalt, it was actually a very high bulk viscosity magma. So it turns out that it's not just composition that controls the viscosity, but how crystalline. And a basalt can be a fairly high viscosity magma if it is highly crystalline. So we think that maybe bulk crystallinity, bulk viscosity is really what's separating these two groups. But then we also have the problem that Miyakejima, which was a basaltic andesite, did not show this rotation in 2000. And this, again, was a very wet, very crystalline, fairly high bulk viscosity magma. So how do we explain that? So it turns out that to produce this rotation of the stress field, you have to consider the strength of the ambient stress field. And through some numerical models, we show that there is a very strong influence of the difference in magnitude between ambient maximum compression and ambient minimum compression. And if that difference is big enough here, you can actually override the tendency of faults in the walls to rotate their p-axis. And so basically suppress or lock seismicity in these zones rather than producing earthquakes with a rotated fault plane solution. And you get this characteristic kind of dog bone shaped area where you would expect seismicity to occur in these cases. And this is pretty clearly what is going on at Miyakejima, even though it's a high bulk viscosity. We saw this very beautiful dog bone structure, suggesting that it was responding, it was a dike intrusion within a very strongly deviatoric stress field. So this is what we see spatially, this expected pattern. And then just also looking at the strain rate map of Japan, Miyakejima, which is located down here, is located in one of the volumes of crust on Earth that experiences some of the strongest deviatoric ambient stresses. So this is very consistent with telling us that the tectonic stress magnitude makes a difference as well as magma viscosity in terms of whether or not we see this stress field rotation during precursory volcanic sequences. So that's a problem. And we weren't able to really separate these two things out. Is the rotation occurring or not occurring because of bulk viscosity or because these volcanoes are in different stress regimes? So fortunately, in 2018, Kilauea volcano in Hawaii did the perfect experiment for us by erupting in the same ambient stress field. First, a very high bulk viscosity magma, and then switching later in the eruption to a very low bulk viscosity, very primitive, low crystallinity basalt. So our hypothesis here was that if bulk viscosity actually matters in generating this fault plane solution reorientation, we should see it at Kilauea during the first phases of the eruption, when there was basalt, andesite, crystalline basalt and andesite coming out, but not during the later stages when it was a very low viscosity basalt. And that's exactly what we observed. This is a very complicated plot, but time is now going up this way, and you can see the different phases. So during the periods of eruption early on, when there was a high bulk viscosity andesite and highly crystalline basalt coming out, we did see rotated fault plane solutions. And then as the volcano switched into erupting low bulk viscosity magma, we saw that the fault plane solutions no longer were rotated. So the black is the non-rotated. So that was a really nice, basically proof that bulk viscosity of magma is a fundamental control on whether we see VT seismicity in response to wall stresses or not. And we were actually able to look at the bulk viscosity of the different phases through this eruption and find kind of a threshold. So that's great. And we can even see that if we zoom out and look at a larger number of case studies where we do see a rotation or don't see a rotation, that there's actually a pretty narrow range in their bulk viscosity that seems to separate them. It's a bit of a gray area, but it's really only about an order of magnitude in bulk viscosity that seems to make the difference. So what we can say then is that if we see rotated fault plane solutions in VT earthquakes prior to eruption, the likelihood is very high that it's a high bulk viscosity magma that's ascending, and there's a higher probability that that eruption will be explosive rather than effusive. If we don't see that rotation, it's a little more complicated because that might be a tectonic stress influence, but we know that we now have linked these rotations to requiring at minimum a high bulk viscosity magma. So that actually allows potentially for forecasts. I'm going to skip that and come to the key points because I want to zoom back out and make a few final comments. So the implications of part 2 are that earthquakes, volcanotectonic earthquakes, actually contain information about the bulk viscosity of the magma that's intruding or ascending prior to eruption. And that this potentially can be used to provide an early indication that an eruption is going to involve higher viscosity magma and potentially higher explosivity and the hazards associated with explosive rather than effusive eruption. And so real-time monitoring of fault plane solution orientations is actually potentially the key to making forecasts of eruption style. Okay, so I just have a few slides left, and I want to zoom back out and just talk about eruption forecasting in general and where we are and where we are going. And I'm going to introduce some exciting new initiatives that I invite you to learn more about. So I want to end by making an analogy between how we forecast volcanic eruptions and weather forecasting. So weather forecasting, which is extremely reliable and very robust today, really started as a process of pattern recognition in a local environment, going back to millennia. People basically observing cloud patterns and linking those to what happened next and making weather forecasts based on very local pattern recognition ideas. That eventually evolved to building instruments to observe patterns more robustly, more objectively. That ultimately led to a network of weather monitoring stations, first in regions, but ultimately around the world. Weather forecasting went through a revolution in the mid-20th century where large computational fluid dynamics models could be run on supercomputers and be tuned by observations across regions. And that ultimately has led to the current state of the art of ensemble forecasts based on very complex data assimilation and physics-driven models. So the analogy is that in volcano monitoring and eruption forecasting, we're stuck we're still stuck in pattern recognition mode. Everything I have talked about today is pattern recognition. We are getting to the point where we have instruments. There are networks of instruments. I showed you studies that were based on permanent networks of instruments on volcanoes. Not all volcanoes are well instrumented. We are starting to make steps into computer-aided forecasts, but really not there yet. So we are maybe generously a century behind weather forecasting in terms of our ability to forecast volcanic eruptions. And this really needs to make a massive leap forward. Part of the issue, of course, is that it's very hard to put instruments and run them on volcanoes. And things are getting better. This is an effort I made a few years ago to try to figure out how many volcanoes worldwide actually have seismometers on them. And it's not a very well constrained answer. I did a complicated look at all of the seismic stations registered in the international database. I then tagged those to volcanoes that have had eruptions since 1980 in terms of the distance of the seismometer to the volcano. I applied some levels of monitoring that were defined by the USGS. So a level 0 volcano has no seismometers within 20 kilometers. A level 4 volcano has more than 6 or 8 seismometers within 5 to 10 kilometers. And really what you can see, the point here is that most of the world's volcanoes are completely unmonitored. And a small number of the world's volcanoes are robustly monitored. So this is a big challenge, even in our pattern recognition mode that we're currently in, that we simply don't have observations from enough volcanoes to fully recognize the patterns and develop models, physics-based models for how volcanoes work and how we can inform models to make better forecasts. So I want to end just by briefly introducing two really exciting ongoing and somewhat nascent initiatives that I'm involved in, and I'd love to talk more about these. I invite you to look and get involved. The first is subduction zones in 4 dimensions. This is a very large scale instrumental effort led by the US and now Chile to study and understand the fundamental processes behind large earthquakes, volcanic eruptions, and landslides. We anticipate instrumenting about 30 to 50 volcanoes in Chile for over a decade. We have partnerships with other international groups. This is a huge effort to overcome our observational limitations at volcanoes to understand how they work and how we can move to this physics-based forecasting paradigm. You can look at the website here, sign up for our listserv. It's a very exciting, big international initiative. The other is one that is more nascent. This is a UK-based charity organization called the Global Volcano Risk Alliance. I recently joined its Science Advisory Board. It is aimed more at operational volcano monitoring and really trying to advocate for better instrumentation, more consistent instrumentation, more consistent approaches to volcano monitoring worldwide. And so I invite you to look at its website and get involved. I think between these and other large-scale initiatives, the next few decades of volcanology are going to be very exciting, hopefully very data-rich, and so a period where it will be a really important time to really push forward on our understanding and our approach to modeling these systems towards a much more modern mechanism of making accurate forecasts of their activity. So I'll stop there, and I'm happy to answer any questions or talk a bit more about these initiatives. Thank you.
Thank you very much, Diana. That was very interesting to see all the seismic signature of volcanic processes, which we don't really understand.
We're doing better. It's getting better.
Yeah, it is.
More data.
More data. Are there any questions? So you can either unmute yourself and ask a question, or put the question in the chat and I'll read it for you. Nobody? Okay, so maybe I'll have one.
Okay.
You showed a slide about the I think the Mont Saint Helene lava domes
Yes.
and the gas. Yeah, this gas emission. Is it really synchronous? Like when you have a high peak of gas emission, or is there some
Some
shift? Or,
lag.
yeah,
Uh,
sometimes like
I think the answer to that question will be clearer in the coming decades. So until very recently, even at Mount St. Helens, gas was measured maybe a few times per year. So it's very difficult. It has been difficult to relate in the way that you suggest gas emission timing to the exact timing of seismic unrest. What's been really exciting in the gas monitoring community in the past decade or so is the development of instruments, particularly the multi-gas instrument, that are meant to run much more continuously and provide higher fidelity, higher rate data. And so that's more like maybe 4 measurements a day. So I don't think we're at the point yet where we can really confidently answer that question. I think it's an important one because there are implications there that you might expect, the gas to change before the seismicity or the changes in gas chemistry ratios to maybe be consistent with the depth of seismicity. But it's really a data limited problem at present. And there are very few cases where there's very high rate gas data during a seismically well monitored eruption or during the longer term inter-eruptive period. But this is one of the things SC4D would also hope to do, to really make multi-parameter measurements like that that are on comparable timescales, so that we can really look at that in detail.
Yeah, I suspect it's also related to the flux also.
Yes.
Yeah.
Which is a very challenging thing to quantify.
Exactly. There are only very few studies which shows you the flux, even for just a lava dome. And they follow the elevation of the lava dome, but you don't automatically have the flux that was associated with this evolution. So yeah.
Yeah, it's some of the hardest data to get, and I say this as somebody who has to carry car batteries up volcanoes and dig holes. I've gone out with the gas instrument people, and it is incredibly labor intensive and complex data to reduce. You have to take into account wind conditions, you have to do it over areas, very challenging data. So there's a reason that there's less of it, because it is really hard. But I think that's part of the revolution that's coming.
Okay. Thank you very much. We have a question in the chat. So at what depths does slow intrusion normally takes place, and what are the geological parameters that characterize the slow intrusion?
Okay. That's a really good question. So I've kind of cut all of these plots off at, well, let's look at the depths. 8 kilometers. So here's my slow intrusion model here. 8 kilometers is slow intrusion is readout. Okay. 35 kilometers. Yeah, this is an interesting one. So I've really focused on kind of the upper 10 kilometers of the crust and maybe slow intrusion from a level that's somewhere in the mid to lower crust to up to the edifice. But obviously that magma that's in the mid to lower crust has to come from somewhere. And just my perspective is subduction zones. And we do occasionally see deeper signals beneath volcanoes. So I didn't talk about this, but we sometimes see deep seismicity prior to or after eruptions that sometimes precedes eruptions, sometimes follows, sometimes it's just there in the background. So ultimately, there has to be a process of magma moving up through the entire system from its origin. So in a subduction zone from the upper mantle, but it becomes very hard to see signals at that depth. We don't generally see deformation. We sometimes see seismicity at those depths, but it's very hard to record in any meaningful, in any way where we can really dig into it. This is a tough question. So in theory, slow intrusion might take place throughout the volcanic system down to the mantle or even deeper in hotspots. What are the geological parameters? This is another one that why does Redoubt behave this way? It's next door to a couple of volcanoes that behave differently. They tend to have more intrusions. I have no idea. I think that's, again, one of the questions SC4D is aimed at. What are the structural parameters or geologic parameters that might be important? Or is it not important? Does it solely reflect differences in the very localized supply from the base of the volcanic system? I don't think we can say very well, like, what geologic parameters beyond the large scale, okay, this is a subduction zone, this is a hot spot, this is a rift, because we see these differences, between two neighboring volcanoes, and it's unclear whether there's a difference in their maybe underlying rock types or structure, or whether there's simply a difference in the supply coming into the base of the system that's very localized. These are hard things to constrain. It's a really good question, very thoughtful. It's a tough one.
Okay. Any other question in the chat or live? No. Okay, so it seems that there is no more questions. We asked you two tough ones.
You did. Good ones.
Yeah. So I think I'm going to close the session here. I'll thank you very, very much, Diana, for this very clear presentation and challenging us in the future, and also our students to go and acquire some data.
I hope there's a little bit of inspiration there, that this is a good time to think about research in volcanology. And thank you for the invitation, and I hope this was useful.
Yes, it was. Thank you very much. So I'll stop the recording.